Okay, so I'm going to start with chapter 3, part 2. We're going to be talking about chi-squares and pedigree. So the chi-square is going to indicate the probability that the difference between the observed and the expected value is due to chance. So the chi-squared is the x-squared value is calculated by doing the sum of the observed minus the expected squared over the expected. For our degrees of freedom, the degrees of freedom are equal to n minus 1, in which n is the number of different expected phenotypes. Example, if your n is 2, the degree of freedom would equal 2 minus 1, so it would be 1. And then this is our table that we'll use, and the table can be found in your book. But let's just say your degree of freedom was 1, and you fell, and your P was like 0.6. Between these two, 0.5 and 0.1. Okay, now that I've given you the definitions and descriptions, I'm now going to try to explain it to you. So here we have the P generation, which is the parental generation, and we're crossing the parent generation. So we have the purple flower, which is homozygous dominant, crossed with the white flower, which is homozygous recessive. And when we cross that, that makes the F1 generation, which becomes like purple flower. So once we do the F1 and it's a purple flower, we then self-fertilize to make the F2 generation. With the F2 generation, we get a 3-to-1 ratio. You get 105 purple and 45 white. You then add those up to get the total progeny, which would equal 150. Once you get the total progeny, you want to do the phenotype, the observed, and the expected. So we know that the phenotype is purple and white. We got that from the P generation. We know that the observed is 105 for the purple and 45 for the white. We got that information from the F2 generation. And then we know that the total is 150. So to find the expected, we just use the information that we already know. You know that it is a 3-to-1 ratio, so you're going to do 3 over 4 times your total progeny, which will equal 112.5 for the purple. And then your expected for the white would be 1/4 progeny, and that will equal 37.5. And then we're going to do the chi-square analysis. So you know that the chi-square is going to be x squared equals the sum of your observed expected over minus your expected squared minus divided by the expected. So we're going to do the purple first. You do the observed 105 minus the expected 112.5 squared divided by the expected 112.5. And that gives you 56.25 over 112.5. So your x squared equals 0.5 for the purple. And then you'll do the same for the white, 45, which is your observed, minus 37.5 squared, which was your expected, divided by your expected. And once you do the calculation for all that, you should get 1.5. Then you do 0.5 plus 1.5 equals 2.0. So I added the purple plus the white to get a 2.0. And that is how the chi-square value is calculated. So then we do our degrees of freedom. And our degree of freedom from what I previously told you is n minus 1. So right here we see that our 2, we do the minus 1, so we get equals 1. And then you go back to that table that I showed you at the beginning of the slide, and you'll see that it falls between 0.1 and 0.5. So there's a difference between the observed and the expected value, which means the expected value is due to chance. Problem 2. So in corn, purple kernels are dominant over yellow kernels, and full kernels are dominant over shrunken kernels. A corn plant with purple and full kernels is crossed with a plant with yellow and shrunken kernels, and the following progeny are obtained. The purple full is 112, shrunken is 103, the yellow full is 91, shrunken is 94. So they just gave us our observed right there. What are the most likely genotypes of the parents and the progeny? Test your genetic hypothesis with the chi-square test. So we're going to take this information one by one. First, you want to see what information is required to solve this problem. We need to know which alleles are dominant and recessive, and it tells us up here the purple kernels are dominant, which means that the yellow kernels are recessive. The full kernels are dominant, which means the shrunken kernels are recessive. We need to know the initial cross between the parents and identify the genotype. Once again, they already told us. We need to know the observed outcome of the progeny. And we need to, in which they gave us 112, 103, 91, 94, and the expected outcome of the progeny, which we can calculate, and I'll show you later on the slides how we can calculate with the information that was already given to us. We need the total number of phenotype represented by the progeny. Well, and then we need the total number of the progeny. So they give us all that information already in that question. Okay. Now we need to see what information is provided here to solve the problem. So the information we already have, you can kind of see from the observe that they're very close together. So you already know that's going to be a 1 to 1 to 1 to 1 to 1 ratio, or 100%. They give us the genotype, the phenotype, they give us the cross between parents, and they give us the outcome, and therefore our observe can be calculated. Let's analyze the color and shape and traits separately. We're going to start with the purple full. We're going to start with the purple and the yellow to do the color separately. So big P is going to be purple, and small p is going to be yellow, and then you do a Punnett square. So big P over little p, P cross with P and P. And so then we'll get 1/2 purple and 1. We get dominant for the purple, homozygous recessive for the yellow. And then we do the same thing for the traits. Big S with small s, small s. The big S is for full, the small s is for shrunken, and we get 1/2 shrunken and 1/2 full. That is dominant and homozygous recessive. And you can see with our Punnett square that all 4 traits will be recognized. 1/2, 1/2, 1/2, 1/2. 1/2 purple, 1/2 yellow. 1/2 shrunken, 1/2 full. 2 traits together. So we have big P, little p, big S, little s. So heterozygous dominant purple, heterozygous dominant shrunken. I'm sorry, heterozygous dominant full. And then we have homozygous recessive yellow, homozygous recessive shrunken. I wrote it down here. I'm going to do the chi-square test. So we already know that since each 4 traits were recognized, it's going to be 1/4, 1/4, 1/4, 1/4. To the 1 to 1 to 1 to 1 ratio, and that means you're expecting to be 100, 100, 100, 100 for each. And they gave us our observed 112, 194. And then we do, so then we'll do the chi-square analysis. For the first one, we'll do the observed minus 100 squared divided by 100, which is the expected, and we get equals 1.44. And we'll do it for each one, and our total is going to equal 2.7. We go back here to do our degrees of freedom, and we do 4 minus 1 equals 3. And we do 4 because all phenotypes were recognized. And our 4 represents n, minus 1 equals 3. So if you go back to the chart that I showed you earlier, I can come back to it for you at the very beginning. So we got 3 degree freedom, and then we got 2.7 here. So from that, you can see that there was no significant difference and that it was due to chance. Moving on to problem number 3. Joanna has short fingers. She has 2 other brothers who are identical, both have short fingers. Joanna's 2 younger sisters have normal fingers. Joanna's mother has normal fingers. Her father has short fingers. Joanna's paternal grandmother, her father's mother, has short fingers. Her paternal grandfather had normal fingers. Both of Joanna's mother parents have normal fingers. Joanna marries Tom, who has normal fingers. They adopt a son named Bill, who has normal fingers. Bill's biological parents have normal fingers. And then Joanna and Tom produced 2 children, an older daughter with short fingers and a younger son with normal fingers. So now I'm going to explain to you what this pedigree looks like. So our parent, number 6, Joanna. And then number 5, husband. So this is Joanna. This is Joanna's husband. And then we have 2 and 3. Those are her children that she conceived with her husband. And number 1 is their adopted child. And then we go up to number 2. That's Joanna's mother. And number 1 is Joanna's father. The red indicates the people who have short fingers. The circle indicates females. So Joanna is the mother, and this is her daughter. The square equals males. These are Joanna's identical brothers. And Joanna's father, our parents, Joanna's dad. See that the grandmother also had the gene for short fingers, whereas Joanna's mother and Joanna's grandparents on her mother's side did not. They had normal feet. Excuse me. All right, moving on. What is the most likely mode of inheritance for short fingers in this family? The mode of inheritance would be autosomal dominant. It's not likely that it would be Y-linked because every male in the family would have had the gene and they did not. It's not likely that it'd be X-linked because it would be more prevalent in the females and it just was in the females for it to be X-linked who had the gene. And it's not autosomal recessive because they didn't really skip generations. There was a gene found in each generation, so it couldn't really be autosomal recessive. So autosomal dominant is the mode of inheritance that we got from that. If Joanna and Tom have another biological child, what is the probability that this child will have short fingers? So we saw that the dad had normal fingers, Tom. So he would be lowercase b, homozygous recessive. Joanna had the gene for short fingers. So she would be heterozygous dominant. And then we'll do the Punnett square, big B, little b, cross with lowercase b, and we get 1/2 heterozygous dominant, 1/2 homozygous recessive. So that child would have the probability of 1/2. And that is how you explain chapter 3, part 2 of genetics.